Here is one of the most powerful equations you will ever meet, and one of the most misunderstood. Bayes' theorem. It is the precise rule for updating what you believe when new evidence arrives. It is how a spam filter thinks, how a doctor reasons, and how a rational mind should change its mind. Consider a medical test for a rare disease. The test is 99% accurate. That sounds nearly certain. You test positive. What is the chance you actually have the disease? Most people say 99%. The real answer, astonishingly, can be far lower. Bayes tells us exactly why. The trick is the base rate, the prior. Suppose only one person in 10,000 has the disease. That rarity is your starting belief before any test. Bayes' theorem insists we take it seriously. A very rare condition, meeting an imperfect test, produces many more false alarms than true cases. The formula ties it together. The probability of the disease given a positive test equals the probability of a positive given the disease times the prior divided by the overall chance of a positive. In words, new belief equals evidence times old belief rescaled. Prior times likelihood gives the posterior. So belief flows. Start with the prior, your belief before evidence. Multiply by the likelihood, how well the evidence fits. And out comes the posterior, your updated belief. Get more evidence and today's posterior becomes tomorrow's prior. Belief accumulates one observation at a time. That is learning made rigorous. This is a whole philosophy of machine learning. Bayesian methods treat a model's parameters as beliefs, updated by data. The naive Bayes classifier ranks emails as spam using exactly this rule. And any model that gives a probability and refines it as data comes in is walking in Bayes' footsteps. Evidence in, belief updated. So Bayes' theorem. It updates a prior belief into a posterior in light of evidence. Ignore the base rate, and even a great test can badly mislead you. Posterior equals likelihood times prior normalized. Now we turn from single beliefs to summarizing whole datasets. Next, statistics, Chapter 21.